I was working as assistant chief pilot for Continental Express in Cleveland. That day the chief pilot happened to be out of the office, so I was responsible for the safety of the operation. One of our Beech 1900 pilots came in the office and reported to me that on approach his aircraft was acting extremely sluggish and in fact took 20% more power to maintain VREF that day. We went out and took a look at the aircraft. It was covered in ice, about 1.5 inches to 2 inches ice all over the airplane. The boots were clean, but behind the boots was just solid ice. So we went in the office, we took a look at the METAR, the TAF, pilot reports. There were no indications of ice in Cleveland for the day, or at that time. So we gave dispatch a call. And of course, looking at the same reports we were looking at, there was no reason that departures couldn't leave as scheduled. However, I made the very difficult decision to delay the flights until the weather improved. It was difficult because that's extremely expensive for an airline to delay or cancel flights. But I believe I made the right decision for the safety of the operation. And in fact, later that day, we found out there was a fatal aircraft crash within 100 miles of Cleveland, and that crash was due to icing.
Supercooled large droplet icing, better known as SLD icing, is a potentially hazardous icing condition that should command the attention of all pilots. Examples of SLD conditions at the surface are freezing rain and freezing drizzle. But it is possible for SLD to exist only at altitude and not reach the surface. SLD can appear in cloud as well as below. Typical icing events involve supercooled water droplets, but the large droplets of SLD can be 10 to 100 times larger in diameter. These larger droplets can impact a much greater portion of your aircraft, including aft of the protected regions. Flight in SLD conditions can quickly lead to severe icing. This video will present the latest SLD icing information for pilots of all aircraft types. It should be used to supplement your company's procedures and regulatory requirements. Our goals are to enhance your awareness of SLD conditions and help you make better decisions. In this video, we'll discuss the event that motivated regulatory guidance and research into SLD conditions, the conditions required for aircraft certification, and how SLD exceeds those conditions, the possible detrimental effects of an SLD accretion on performance and handling, cues to identify an SLD encounter to facilitate an early escape, and finally, when, where, and how SLD forms.
Say all 68 people aboard, passengers and members of the crew, are presumed dead. News 8's Rick Hightower is in Newton
One
County
fatal accident linked directly to SLD icing occurred near Roselawn, Indiana in 1994. An ATR-72 was holding at 10,000 feet with all ice protection systems activated, flaps deployed, and autopilot on. They were in SLD icing conditions. When the flaps were raised during descent, the aircraft angle of attack exceeded 5 degrees, and the aircraft went into an uncontrolled roll. The NTSB determined the probable cause to be loss of control attributed to a sudden and unexpected aileron hinge moment reversal that occurred after a ridge of ice accreted beyond the de-ice boots. There were no survivors. Following this accident, the FAA issued airworthiness directives against many turboprop aircraft with the warning that severe icing may result from environmental conditions outside of those for which the airplane is certificated. They go on to say flight in freezing rain or freezing drizzle may result in ice buildup on protected surfaces exceeding the capability of the ice protection system or may result in ice forming aft of the protected surfaces. This ice may not be shed using the ice protection systems and may seriously degrade the performance and controllability of the airplane. The ADs further require the pilot to exit the conditions immediately and request priority handling if necessary. The Roselawn accident also launched an international effort to better understand and predict the meteorological conditions that produce SLD, as well as a mandate to build ways to ensure safe operations in or around SLD conditions. To this end, NASA teamed with the FAA, the National Center for Atmospheric Research, the Meteorological Service of Canada, and the National Research Council of Canada to explore and characterize SLD icing. An extensive flight test program using NASA's Twin Otter icing research aircraft was initiated in the Great Lakes region during the late 1990s. The information from these flights and continuing research activities has greatly improved our understanding of this icing condition. All aircraft certificated since 1973 to fly in icing conditions have ice protection systems designed to the same requirement. The icing certification envelopes define cloud characteristics that relate the amount of water in the cloud to a measure of the droplet size. The median droplet size range is between 15 and 50 microns MVD, or median volume diameter. The diameter of a thin human hair falls within this range. SLD conditions are those with droplets larger than 50 microns. Freezing drizzle droplets range up to 500 microns, or the size of a 0.5 millimeter mechanical pencil lead. And freezing rain droplet sizes are greater than 500 microns. That means the ice protection system on your aircraft is not certified for droplets the diameter of the lead in this pencil. Flight in SLD is an exceedance condition. Your ice protection system may not be able to safely protect the aircraft in these conditions, even though it is certified for flight into known icing. While this video focuses on large droplet icing, you should also realize that there are other ways to exceed the icing certification envelope. For example, exposure to dense clouds containing large amounts of water can also lead to a severe icing encounter. Recall the FAA Aeronautical Information Manual defines severe icing as the rate of accumulation is such that de-icing or anti-icing equipment fails to reduce or control the hazard. Immediate flight diversion is necessary.
Look, the bottom line is, it doesn't matter if the icing you're in is caused by SLD or a cloud with lots of liquid water. If the ice protection system can't control the hazard, it's severe icing. Call it severe to ATC and work to get out immediately.
SLD icing contains the larger, heavier droplets, which have more inertia and can coat much more of the aircraft's surfaces. This is true regardless of aircraft size. SLD accretions are of particular concern on wing and tail surfaces. Unlike the smaller cloud-sized droplets that strike within the protected regions, larger droplets can impact from the leading edge to well aft of the ice-protected regions. While the de-icing or anti-icing protection systems will clear these areas, the ice that is formed aft will remain. This can form a ridge at or aft of the protected non-protected junction. This change in the shape of the flight surface may not be immediately dangerous, but could become so during configuration changes or when enhanced performance is required, such as approach and landing, a missed approach, or an emergency situation. This is why SLD icing can be substantially more hazardous than normal icing. The research efforts and regulatory guidance into SLD conditions have focused on turboprop rather than jet aircrafts. Jets typically do have advantages in icing conditions, with larger airfoils, higher climb rates, excess thrust, power-assisted controls, and anti-icing systems. However, the jet pilot should not feel immune in an SLD encounter. One potential disadvantage is the lack of visual and tactile cues. Without a reliable means to monitor for SLD, you could be exposed for a longer period of time. This can lead to a ridge or other significant SLD accretions.
It really doesn't matter what kind of aircraft you're flying, turboprop, regional, corporate jet, or big iron. When you're in SLD, you have no idea how well the ice protection system is performing. In most cases, you're probably accreting ice after the protected area. You don't know what effect the resulting ice accretion will have on aircraft performance and handling. Most importantly, handling. The best defense is to avoid it if possible, or if you get in it, detect it early and get out.
The ridge and extensive ice formation on non-protected areas of the airframe can lead to a substantial increase in drag. For propeller-driven aircraft, this can result in a situation where thrust is no longer sufficient to maintain level flight, and a descent must be initiated to preserve airspeed. SLD accumulations, particularly the ice ridge aft of the protected areas, may also significantly alter the wing's lift characteristics. The ridge will disrupt the airflow and create a region of separated flow. Wind tunnel tests were conducted on a NACA 23012 airfoil with a simulated SLD ice shape. The measured lift and angle of attack show a dramatic decrease in the maximum lift capability and stall angle. Flight tests in natural SLD icing with a Twin Otter aircraft substantiate this degradation. Here are the lift versus angle of attack curves, comparing a clean wing to a freezing rain and freezing drizzle encounter. For these particular encounters, the maximum lift was cut nearly in half. This greatly reduced maximum lift translated to roughly a 30% increase in stall speed. Note these results are airfoil specific. Your aircraft may respond differently. These SLD accumulations may affect aircraft handling characteristics as well. Especially on aircraft with unboosted controls, an ice ridge in front of a control surface can lead to unusual or abnormal control responses. If the separation bubble grows aft, it may cause the control surface to either auto-deflect or become ineffective and lead to a roll or pitch upset. Cues to an impending wing stall or upset include airframe buffet, unusual roll control response, or uncommanded roll or pitch motions. Should any of these cues occur, reduce the angle of attack of the wing. This can be done by pushing forward on the yoke and adding power. It's more important to retain control of the aircraft than worry about altitude. If practical, return to the previous safe speed and configuration. If the aircraft does stall, you must immediately reduce the angle of attack. It is imperative to regain control of the aircraft. Any subsequent increases in angle of attack following the initial recovery must be executed with care to avoid a secondary stall. SLD accumulations may cause the horizontal tailplane to stall at a lower local angle of attack as well. As with the wing, recovery from a tailplane stall requires reducing the local angle of attack. In this case, by bringing the nose up. This can be accomplished by pulling the yoke back and raising flaps. Consult other resources, for example, the NASA video tailplane icing, for further discussion on this phenomenon. Of course, any degradation in handling qualities is more likely and more significant during any phase of flight where the aircraft is being configured or maneuvered at low speed. That is climb out, holding, approach and landing. Also, SLD can result in ice accretions on portions of propeller blades, even those with an ice protection system, and may result in thrust losses. Monitor your airspeed, as it can rapidly decay even when airframe accumulations seem small. The sooner you detect you're in SLD conditions, the sooner you can act to escape. The extensive ice accumulation typical of large droplets may be helpful in visually detecting an SLD encounter. A generic cue cited in the ADs is unusually extensive ice accreted on the airframe in areas not normally observed to collect ice. As common visual cues are identified next, it should be noted that some of these may not be available in your aircraft. On some aircraft, the most immediate and obvious visual cue of SLD is ice forming on unheated or unprotected cockpit side window panels. Another visual cue is a ridge of ice on the wing at the protected-unprotected junction, or ice aft of the protection system. Of course, a normal icing encounter would accrete entirely within the protected region. Photographs of NASA's icing research airplane show how ice can form beyond the areas protected by the pneumatic de-icing boots. Icing tanker tests of the ATR-72 conducted shortly after the Roselawn accident also illustrate this ridge. After testing, the ATR-72 was modified with a larger de-icer boot that provided more chord-wise protection. Aircraft with heated leading edges may also experience ridge formation aft of the heated areas. Here are images from a research test in NASA Glenn's icing research tunnel. A thermal heat system at flight conditions was tested in an SLD environment. Note the ridge beyond the protected region. On turboprop aircraft, propeller spinners are another area to monitor. Compare the SLD versus normal icing accretions. Note how much further aft the ice appears in the SLD case. Other visual cues of SLD may also include unusual or more extensive ice formations than normal on windshield wipers, control horns, nacelles, winglets, or on smaller aircraft, wing struts. Finally, visible rain or droplets that splash or splatter on impact below 0 degrees C ambient air temperature are also signs of large droplet icing. If these visual cues are not available, you'll need to be especially vigilant to tactile and instrument cues that indicate any hazardous ice accretion. Such cues might include airspeed loss, unusual trim motion or position, higher than normal power settings, non-responsive controls, or unusual feedback in the controls. These cues will be more difficult to detect with the autopilot on, so periodically hand fly the aircraft to confirm normal handling characteristics in any icing encounter. Also realize that any ice-related system, such as an ice detector or a stall warning system designed to account for ice accretion, was certified to and probably designed only for the icing certification envelope. Such systems may not perform their intended function in SLD conditions. Some airplane flight manuals give very specific information about SLD cues and limitations. Familiarize yourself with any limitations or information contained in the AFM about icing and in particular about SLD. If you are in flight and confirm or suspect SLD conditions, carefully monitor the ice protection systems. If they are unable to remove the hazardous ice accumulations, you are in severe icing. You must exit the condition immediately. An altitude change of 2,000 to 3,000 feet most likely will take you out of the SLD environment, even if you remain in the cloud. The safe altitudes, of course, are dry air or where temperatures are above freezing. Report the hazardous conditions and request priority handling to exit the icing if necessary. Unless you can conclusively confirm that all the ice is shed, sublimated, or melted away, you should assume that the airframe will continue to have ice aft of the protected areas for the remainder of the flight. Make every effort to avoid a subsequent icing encounter of any kind. Since SLD ice shapes have formed on the aircraft surfaces, this contamination can catch smaller droplets that a clean surface wouldn't. The ice shape will continue to grow in size and potential hazard. With ice on your wings, your angle of attack becomes very important. Of course, the safest flight condition is to remain at a low angle of attack or in cruise. If it becomes necessary to increase your angle of attack with the SLD accretion, for example holding, approach, or landing, follow your AFM for these procedures and icing conditions. The holding guidelines may limit flap deflection, and the approach and landing may call for an increase in airspeed. Increasing AOA with an SLD ice shape can become hazardous to the point of a control anomaly. When and where can you expect to find SLD? This map depicts the potential of encountering SLD conditions in North America in the winter. It is based on surface observations and balloon soundings gathered over a 14-year period and analyzed by NCAR. While the SLD potential shifts predictably in latitude and altitude throughout the year, there are consistent regions where you are more likely to find SLD. These are in the Pacific Northwest and in a wide swath from the southern high plains through the Great Lakes region into the Canadian Maritimes. While this map shows the hot spots for SLD, it is the local atmospheric conditions that determine whether or not you'll have an SLD encounter. This study also found that for the most part, SLD conditions were less than 3,000 feet deep, whether they were at the surface or at altitude. Furthermore, SLD was found mostly below 12,000 feet. Finally, understanding how SLD develops in the atmosphere may assist you in developing your avoidance and exit strategies. There are two SLD formation mechanisms: temperature inversion and collision coalescence. Temperature inversions are typically associated with warm and stationary fronts. Ahead of these fronts, snow falls into above freezing air and melts, forming liquid precipitation. The liquid precipitation continues to fall into freezing temperatures below, forming freezing rain and, occasionally, freezing drizzle. In some cases, the rain or drizzle freezes to form ice pellets that fall to the surface. In this case, the greatest potential for encountering SLD is from the bottom of the above freezing layer all the way to the surface. Research indicates this layer is generally less than 3,000 feet deep, but it has been observed up to 7,000 feet deep. Pilots are more likely, however, to encounter SLD formed by collision coalescence. This process, recently recognized as an aviation hazard, occurs when droplets collide within a cloud and coalesce into larger droplets. Research has shown that SLD clouds of this type are usually relatively warm, low-altitude clouds. Look for cloud top heights below 12,000 feet and cloud top temperatures warmer than about -12 degrees C. In this case, the SLD layer is usually less than 3,000 feet deep. Be aware, however, that this type of SLD can occur above 12,000 feet. Regardless of how the SLD is formed, exit strategies may require larger altitude changes. While SIGMETs identify areas of potential severe icing, there are tools that better pinpoint areas and altitudes where SLD may form. These tools are available on the Internet from the Aviation Weather Center. One is at the Aviation Digital Data Service. On the icing page, you can check the SLD potential in addition to the icing potential at various altitudes. At the same time, you can check for airmets, SIGMETs, and icing PIREPs. You can also select the Flight Path tool and check for icing along your intended route. Convenient altitude displays of the same SLD and icing potential data are also available. To summarize, supercooled large droplet icing involves a greater risk than normal icing. The large droplets can coat much more of the aircraft and may form a ridge of ice aft of the protected areas on the wing and on the tail. These SLD accumulations may dramatically reduce aircraft performance and alter the handling characteristics. If you encounter SLD conditions in flight, early detection and exit will help minimize the risk. Know where to look on your aircraft to quickly detect SLD accretions. If visual cues are not available, carefully monitor your instruments and the handling of the aircraft. If a speed or configuration change results in an unexpected or abnormal aircraft response, return to the previous safe configuration and speed. When the aircraft is stabilized, you can assess your options and decide on the safest course of action. To exit SLD conditions during cruise, an altitude change of 2,000 to 3,000 feet will probably be sufficient. But realize that extra caution is warranted during holding, approach and landing, and if attempted, takeoff and climb. You are most vulnerable to SLD accretions during these phases of flight because you're asking for a lot of performance from the wing when you're low, slow, and configuring. At the same time, your escape options are more limited due to traffic and terrain. You'll need to assess the environmental situation and the current capabilities of your aircraft to determine the optimal path to safety.